Welcome back to the second video for January 20th. The main purpose of this video is to talk through the instructions for Lab 2. Lab 2 starts on page 13 and it goes through and including page 16. So it does include those calculations on page 16 of the lab manual. So we'll get to that in just a second. But I do want to make just a quick note before we go into that, a quick note about next time, our next class session on Monday. So in the last video, I mentioned that these concepts that we're talking about, the voltage divider and Ohm's law, they're just tools, like a screwdriver. They're just tools to help us solve circuit analysis problems. Like if we wanted to find the voltage drop across a particular resistor or the current through a particular part of the circuit, and so on and so forth. Ohm's law and voltage divider are just things, they're just tools that will help us solve for those different aspects of the circuit. The thing I want to mention now, though, is that you don't have to go too far into the field of electronics before you encounter circuits that you just can't solve with Ohm's law and voltage divider, or simple conceptual things like we talked about in the last video. It just doesn't work. There's just no way of solving them using those relatively simple tools. There is a more advanced or capable way of solving them, and it's a better set of tools, and that's what we're going to learn on Monday. Those tools are called Kirchhoff's voltage law and Kirchhoff's current law. They go hand in hand, and they're usually abbreviated KVL, Kirchhoff's voltage law, and KCL, Kirchhoff's current law. So I don't want to scare you or intimidate you, but I will say that those probably tend to be some of the more challenging concepts, and Lab 3 is probably one of the more challenging labs, at least in the first third of the semester. So it comes up quickly, right? We're only going to be in lab in week 3, but I'm already telling you that's one of the more challenging labs, and it is. But it fits in with this section of the class about circuit analysis. So that all being said, what I am strongly recommending that you do, because it will help you out very much for the next class and the next lab, is to read pages 17, 18, 19, and 20. It's 3.5 pages on KVL and KCL. And you might want to read it more than once. You might want to read it a couple of times to really let it sink in. Oftentimes that's what I would do. In reading textbooks, sometimes you have to read stuff more than once. So it's not a lot of text here, but really take your time reading it and try to understand what it's saying. And then, of course, we will do a whole bunch of examples, and I'll be happy to answer any questions that you have. And I'll do my best to help you understand this. But I'm telling you, it'll be a lot easier for you to understand if you come into class next Monday with already sort of a grasp of what it is we're going to be doing in KVL and KCL and in Lab 3. All right, so that's my strong recommendation, is read that part of the lab manual. I mean, I always recommend that you do that. I always recommend that you read the reading in the lab manual before class, but I'm pointing this out in this video particularly because it's especially important for the next class when we talk about KVL and KCL. All right, enough about that for right now. Let's go ahead and get into Lab 2, and so I'm going to switch over to the document camera. All right, Lab 2 in a lot of ways is very similar to Lab 1 in the sense that you're going to use Tinkercad, and there are also going to be some calculations that you'll do on the side in addition to Tinkercad. So once again, just like in Lab 1, anywhere where it says measure, I want you to do that in Tinkercad. Anywhere where it says calculate, down here, I want you to do that not in Tinkercad, just calculate it with a scratch piece of paper or something. All right, so you're going to be building this circuit. You're going to measure the total resistance with, and then you're going to be measuring voltage drops using the multimeter in Tinkercad. Let me say something about this real quick. Here's a power supply that actually looks very similar to the one in Tinkercad also. You're going to want to set the voltage to 20 volts, and I can see how there might be some questions about the current setting on Tinkercad. So when you set the current value in Tinkercad, what you're setting is the maximum current that power supply can provide. So it's not going to automatically provide that current. It is gonna automatically provide that voltage. So you're telling it what voltage to apply to this circuit, and it's going to provide that voltage to this circuit, and then it will allow as much current as you set it to, up to that amount of current. It will not exceed that amount of current, okay? So when you're doing this in Tinkercad, like I think I showed in video 2 from the last class session with the demo of Tinkercad, I would probably just set the current value to like 5 amps. That should probably be plenty for anything we're going to do in the next couple of labs, I think. I can't imagine it would go above that. So just set it for now. For this first part of lab 2, set it for 20 volts and 5 amps. And you'll see it's not going to take that much current. It's going to be a lower current value. Okay, so just wanted to clarify that. I could see some questions coming up about that. So all of these values should be measured. All of these values should be calculated on a piece of paper. Answer some conceptual questions here. Then we're going to measure current. Remember that to measure current, and once again, you can go back to the second video from last week where I did the demo of Tinkercad. And I did a demo of almost exactly this, of page 14 and page 15. I did both of these in the demo of Tinkercad last week. So you can see how I did this. Just remember that to measure current, you've got to break the circuit. Because if I just had the circuit right here, just imagine that's not there for right now. If that wasn't there and I had a wire right there, and I tried to measure current, where's my multimeter? If I tried to take my multimeter and set it to current, and then didn't break the circuit and just measured it like this, most of that current is not going to go through the multimeter. Most of that current is just going to go through the resistor. And so it's not going to work. You're not going to get an accurate measurement of current. In order to get an accurate measurement of current, you got to break the circuit like that, and then connect one side of the break to the multimeter and the other side of the break to the other side of the multimeter, so that all that current actually goes through the multimeter and then to the other side. Voltage is different. To measure the voltage, you don't have to break the circuit. To measure the voltage, you really can just go like that, even while the circuit is energized. Okay. That also often leads to confusion. All right, this over here, it says to calculate it. So you can calculate them and put it in there. And then in this step, the top of page 15, this is very similar to what I did in the last part of the Tinkercad demo last week. So if you want to measure down here the current through each one of these resistors, which you need to, then one by one, or I guess you could do it, you have unlimited multimeters in Tinkercad, so you could do it all at once if you want to, with 3 different multimeters. Or you could do it one by one, where you break the circuit here and connect a multimeter measuring current, and then you could stop it and you could reconnect that, break it right here, and connect a multimeter, and then for that one. So anyway you do it, just make sure that you've got it set up correctly to measure current through here. All right. These should match up, I mean, almost identically. You know, maybe a little bit of rounding error, but almost identically between all of these values right here. Okay, so measured, use Tinkercad, calculate, use your calculator. All right, and then similar to Lab 1, the last page, this is page 16 in the lab manual, the last page is just calculations. You don't need to build these in Tinkercad, unless you want to, that's fine. It'd be a way to test your calculations and verify your calculations. All right. Due date is specified in the lab manual, so check that out. Oh, once again, for all these Tinkercad problems, labs, remember to change the file name to your last name space lab space 2 in this case, and then take a screenshot of the last one that you build in Tinkercad. So it would be this one. Yeah, I don't want to mess this up by saying the wrong thing like I did last time in lab 1. It should be this one. So once you build that in Tinkercad and you connect multimeters or a multimeter, depending on how you measure it, take a screenshot of it and then upload that with your lab, your completed lab, into ReggieNet. Okay, I almost forgot about the trampoline problem, but I didn't. So before I talk about that just a little bit more, let me show you a video that maybe changes the way that you think about this. So here is a YouTube video that I think is a pretty awesome video. Did you see that spark in between that conducting metal pole the worker was holding and the transmission line? So these are energized. All right, so watch that again. There's going to be another spark again as he pulls away. Yeah, do you see that? All right. All right, so what's going on? I got to cancel that video. I was going to play something else. All right. Okay, so what's going on? The helicopter moves in close to the transmission line. That is a dangerous job for that pilot. You know, if he makes one false move, he's going into the transmission line. But he's got to get really close to the transmission line in order for those workers to get out on those transmission lines to do some inspections on them. And the thing is that that helicopter is not connected to ground, right? So it's not connected to ground, so there's no path to ground, so there's no complete circuit, right? So that is the crucial detail. There's no path to ground, therefore there's no complete circuit. Initially, as the helicopter is flying through the air, it's at a different potential. You know, there is static electricity, so it builds up some small voltage. But it's at some potential, and the transmission lines are at some potential. But there's no path to ground. Even when they touch, when there's that conductive that pole they reach out and touch the wires with, because they don't want to get that static shock from their foot or their hands when they touch it, they use that conductive pole, which is connected to the helicopter. But then once they're at the same potential, the helicopter and the transmission line, then those workers can just step out onto the transmission line, even though that transmission line relative to ground might be at hundreds of thousands of volts. So that relates to our question about the transmission line, because if you jumped up and were able to grab onto the transmission line, there's no path from your body to ground, right? So you would not be able to complete the circuit, assuming you're jumping high into the air, right? If the transmission's lying on the ground or just above the ground and you touch it while your feet are on the ground, different story entirely, right? But as long as you're way up in the air, you grab onto it and you are not touching anything else, your legs don't touch the transmission line pole or something like that, as long as you're just hanging there, dangling from the transmission line, I wouldn't try it. I'm not suggesting that you try it, but you should be okay. And real quick, here's another way of looking at that. All right, so we can actually draw a little model. So here, here's the transmission line. Here's the transmission line, and here's my, how should I draw this? All right, here are my hands. How many fingers do I have? I don't know. And here's me. Pretty thrilled that I jumped up on the transmission line. And so here's me on the transmission line. And I'm grabbing onto the transmission line. Now, that transmission line has some resistance, right? It has some resistance. It's a wire. So although we said that in the lab we can make the assumption that wires have zero resistance, in reality it's not zero, but it's some very small value of this transmission line, 2 feet of that transmission line between my hands. So it has some resistance. And likewise, my body has some resistance also, right? So there's some resistance from here through my body, right through my heart, probably, and then back up like this. So what is this? This is a parallel circuit. We have just constructed a parallel circuit. And we said in the first class session that kind of a worst case scenario might be around 500 ohms for a human body, whereas this is probably a big fat transmission line, so it has very low resistance, much less than 1 ohm. It's not zero, but it's much less than 1 ohm. So if this has a resistance of 500 ohms to my body, and this piece of transmission line between my hands has a resistance of much, much less than 1 ohm, then we can think about how much current is going to go through here as compared to here, right? There will be some current that goes through here. It's not zero, but the vast, vast majority of the current is going to keep on going through the transmission line, not through my body, all right? I probably still wouldn't try it. It just doesn't seem like a smart thing to do. So if you try it and you get badly injured, don't come back to me and complain to me. But you should be okay. This is the exact same reason why birds can sit on transmission lines, right? You ever read the books, the pigeon books? Probably not. They're kids' books. But anyway, this looks like the pigeon. Anyway, we have a resistance right here of the transmission line, and then we have the resistance of the pigeon. And the pigeon or the bird can sit on the transmission line because the resistance between the bird's feet is much, much, much less than the resistance through the bird. So the amount of current going through the bird is not zero, but it's very, very small compared to the current going through the transmission line wire. All right, so that's a fun little thought experiment. All right, so that'll do it for today. You now have enough knowledge to do Lab 2, so you can start doing that. Check the due date on the calendar schedule, and let me know if you have any questions. Otherwise, I'll see you next time. Have a good week.